So now that we have defined the notion of convergence of a sequence rigorously, and we have seen how this definition works, let us now introduce some topological terminology and see maybe a simpler way of thinking about this, or an alternative way which turns out to be easily generalizable to other spaces, or more naturally generalizable. So this notion of almost all is super important in mathematics. So suppose that we have a sequence, it's an infinite sequence, and of course finitely many elements are not that interesting. We're interested only in infinitely many sequence elements, and we can take a sequence and actually ignore finitely many elements of the sequence, and it will not affect the limit, as we will see. And so we say that a certain property of a sequence is satisfied by almost all the elements of the sequence, almost all, if it is satisfied by all the elements except for finitely many. So this is important. Okay, and so now let us think of distances and what it means to have a distance function. So let us now ask a question, right? Suppose that we are in this three-dimensional space. What is it a ball? So a ball of radius r is the collection of all the points in space whose distance from a fixed point, which we call a center, is smaller than some number r, which is called the radius, right? So this is a ball, and we can define a ball in any metric space, right? In any space where we can measure distances, we can define this general notion of a ball by saying, given a center point, we can now look at all the points whose distance to this point is smaller than this radius. This will be called an open ball, right? And this is super important, and we will see why in terms of convergence. Okay, so let us now make this definition. So let XD be a metric space, that is a space where we can measure distances. So a natural generalization to a ball in the space would be a round centered at the point x0 with a real number r, which we think as the radius of the ball. So we define the open ball as the set of all points whose distance from x0 is smaller than r. So of course it's a natural way of generalizing balls, and metrics can be weird, and metric spaces can be weird, and balls can be also weird on those spaces, but nevertheless some key properties are maintained in this generalization. So it's important to introduce this abstract thinking, I think, early on. Okay, and so this this ball is the open ball because we do not include all the points whose distance from x0 is exactly r. We take all those that are smaller than r, and this is called the open ball, and it will use it. It will create a role in defining what it means for a set to be open. It turns that this is our basic open set. It's our measurement to being open in a sense that we'll see. And when we take all the points with the boundary points, including the points whose distance from x0 is exactly r, this is called the closed ball. And those are two very important examples of what we call in topology or in mathematics open sets and closed sets. But okay, so and of course in our Euclidean space or in the space R3, the three-dimensional space, those are very intuitive, and they coincide with our intuition, provided that we take this Euclidean distance function, right? So that we measure the distance between 2 points in space, just with our familiar way, or with the square distances formula, right? And the square root of that. Okay, so of course, in a plane, an open ball in the plane will be the locus of all the points, and this is our distance function, right? So if we would want to generalize the notion of convergence of a sequence of points in the plane, then we would take this d to be our distance function, and the definition goes without changing. We just change the distance function. We say that in the plane, this is our d, this is our distance function, and convergence with respect to this distance, and it's the same definition for the plane, or for the three-dimensional space, or for any n-dimensional Euclidean space. And so this open ball, you see that we do not draw the boundary, so those boundary points are not included, and this is the Euclidean open ball. Okay, And if we take this closed ball with the boundary included, then this is the Euclidean closed ball, the location of all the points whose distance from this ball with radius r centered at the center point x0, y0. And so, of course, this is the collection of all points in the plane whose distance is smaller or equal than r, than this radius r. And yeah, this doesn't necessarily has to be the origin. This is the point x0, y0 here, right? Okay, and so what does it mean to have a ball in one dimension, a ball in R, right? So this is the collection of all points whose distance from x0 is smaller than R with respect to this distance function d on R. But this means that this open ball coincides with this open interval. This is exactly what it means to take all the points on the real line whose distance from x0 is smaller than r. They all lie between x0 plus r and x0 minus r. So this is our open ball on the real line. And similarly, we have the closed ball, which is this closed interval of radius r. Okay, and sometimes it is convenient to call this the R neighborhood of x0, or in particular where R is this positive epsilon, this positive number, then we would call this epsilon neighborhood. Okay, and so now let us restate and give an equivalent definition of convergence. So suppose that we have a sequence an. It could be a sequence of real numbers. Here it's understood that this is a sequence of real numbers, but it really generalizes to arbitrary spaces where we have distance on, or even just a topology, but let us ignore topology for now. Then we say that the limit of an is L if every epsilon neighborhood, so epsilon neighborhood is this ball with radius epsilon centered at L. So every ball centered at L, I mean all the points that whose distance from L is smaller than epsilon, contains almost all the elements of the sequence. Okay, it contains all the elements except maybe for finitely many. And so now when we give two definitions to the same thing, let us show that these two definitions are equivalent. So this is in fact a theorem. So the definitions for the limit of the sequence that were given here are equivalent. And let's prove it. So suppose that we have sequence an that converges in the sense of the first definition. So this means that for every positive epsilon, there exists n of epsilon, such that for every n that is greater than n of epsilon, an minus L is smaller than epsilon. This is the original definition. But this inequality is equivalent to saying that an is between L minus epsilon and L plus epsilon, which is equivalent to saying that an is lying in this interval. But this, oh, sorry, it has to be plus here. It's a typo here. I will fix it. So between L minus epsilon and L plus epsilon. And therefore, this is the epsilon neighborhood of an, right? But this, this epsilon neighborhood contains all the elements of the sequence except maybe for the finite collection a1 up to an. So those elements a1 up to an, they may not satisfy this inequality, but there are finitely many of them, and therefore they may not lie in this epsilon neighborhood. All elements starting from n of epsilon plus 1 and on has to satisfy this inequality, and therefore has to lie in this epsilon neighborhood. And so this epsilon neighborhood contains almost all. So it has to contain all the elements of the sequence except maybe for those, right? So this epsilon neighborhood contains almost all the elements of the sequence except maybe for finitely many. And since epsilon is arbitrary, this means that every epsilon neighborhood contains almost all elements of the sequence. This is how strong this definition means. And yeah, this is what I have said. So if the sequence converges according to the first definition, it also converges according to the second definition. Now suppose that it converges according to the second definition, right? We need to show that it converges according to the first one. So this means that let us pick an epsilon, right? And let us now pick an epsilon neighborhood of L. And so the second definition says that every epsilon neighborhood of L contains all the elements except for finitely many elements. So now let us define this set A, which will be the set of all the natural numbers within the natural indices, such that a k lies outside this interval. Now, since an converges according to this definition, this set is finite, and as a result, every finite set has a maximal element. Now, the maximal element of this set A may depend, of course, on epsilon. So let us call the maximum element of A, let us denote this by n of epsilon, and this is it. Only elements of the sequence whose indices are in A may lie outside this epsilon neighborhood. All other elements, in particular for every n that is greater than this, they must lie inside this epsilon neighborhood, right? And so this means that for every epsilon, there exists a natural number n of epsilon, which I said how to define. It's just the maximum of this finite set. And then every n that is greater than n of epsilon, for this we must have that the n lies in this epsilon neighborhood, which means that this is actually equivalent to the distance of n minus L being smaller than epsilon, that this inequality is satisfied. So we have proved that. So this is truly equivalent. So now we can generalize this quite naturally to convergence in arbitrary metric spaces where the only thing that we have is a way of measuring distances, and this space can be very, very abstract. And even this condition can be relaxed on having a metric. It's just what we essentially need is the notion of neighborhood, or an open neighborhood, as we will see, to define convergence. And this is something very strong. This is a vast generalization, and I'll tell you why generalization is important, because when you generalize something, on the one hand, it's more abstract and harder to work with. On the other hand, once you prove a theorem for something abstract, you have proved a multitude of theorems, a lot of theorems for many, many, many cases, right? And this is the power of mathematics, is actually this generalization and abstraction. And so it's important, to early on introduce this, on the one hand, abstraction, and on the other hand, to show its connection to concrete cases. So now let us define the convergence in a metric space. So let xd be a metric space, and let an be a sequence in X, right? And so we say that this sequence an converges to some point x0, which is an element of X, and we write this in the same way. X can be a very abstract space. If for every epsilon we can find a natural number such that for all n that is greater than n of epsilon, the distance between an and x0 is smaller than epsilon. And equivalently, this means, right, that for every epsilon there exists n of epsilon such that for all n that are greater than n of epsilon, we have that a n lies in the epsilon neighborhood of x0. And so this general notion of saying that a sequence converges to a point x0 in limits in a metric space. So to say that a n converges to a point x0 in a metric space is the same as saying that every epsilon neighborhood of this point, or open ball around x0 with a radius epsilon, contains almost all the elements of the sequence. That means all except for maybe finitely many. Okay, and so let us now study this important set, the open sets, those super important sets of open balls, because we have seen that with those we can define the notion of convergence, right? And all we need to define those is a metric. And we'll see that there are other generalization. So those open sets can be even defined without the notion of distance, but all in its right time. So for now, suppose that we're still in R, right? And so let's see what are the key properties of those open balls in R, but in fact they hold for any metric space. So what we see here is that for every point x in this open ball, which is in fact just an open interval, we can find an even smaller open ball that is centered at x and is contained in this original ball. That is, so if we say this is radius delta, then the ball around x with radius delta is contained in this ball. So let us first prove this. So the idea, of course, if we were to visualize this, is that this open is interval, and so x never reaches the boundary. If we had this closed interval, right, and we take the edge point, then every neighborhood of this point x will contain elements inside the interval and outside the interval, right? Every neighborhood. But since this interval is open, then there is, for every point that we choose, it has positive distance to the edge, right? And then we can take a neighborhood with radius that is smaller than the distance to the edge. So let us see how do we do it. Suppose that x lies in this ball of radius r around x0. That means that basically this is the open interval x0 plus r and x0 minus r. And so this is equivalent to saying this. And so what I wanted to show that then I can find a ball around x0 such that for all points in the ball around x0 the distance is going to be smaller than r. So it's easier to understand when it's just written. Okay, so suppose that x minus x0 is smaller than r. This means that there exists some positive h, right, such that this is a typo, sorry. H is greater than 0. That's the only thing that I meant for this to be. So let us denote x minus x0. We have this positive h. So let us denote this by r minus h, right? Because x minus x0 is strictly smaller than r, then we can define h by r minus this. Okay. And let us choose this delta to be h half of this distance. Then let's see what we have. Then for every y in this interval of length delta around x, let's see what we have. So first of all, if the distance from y to x is smaller than delta, and delta is h half, right? And in addition, we also have that the distance between x and x0 is r minus h, right? So now let's see if we use the triangle inequality. This is the importance of the triangle inequality to show this property of open balls. Okay. So now suppose that y is any point whose distance from x is no more than delta, right? So we take any such y. And now what we do here, we use the triangle inequality here. We could add we could subtract x here and add x here. And so using the triangle inequality, we see that this is no more than that. But the distance from y to x is smaller or equal to h half. And this distance is r minus h. And so what we have here is r minus h half, and h is positive, so of course it is smaller than r. So what we have proved is that for every point whose distance from this x is smaller than delta, which is h half, its distance from x0 is still going to be smaller than r. And this means that this ball of radius delta around x, or an open interval with radius delta around x, is contained in this ball of radius r around x0. And this is the way to visualize this. So maybe it will be easier to see. So this is x0. So here I took a two-dimensional ball, but we can think of it also as just this interval. So this is the center point x0, okay? And this boundary is not included. These boundary points are not included here. So for any x here, right, I can look at this distance is actually from x to the edge to this. This distance is r, is positive. So I can find an even smaller ball around x0 that is entirely contained in this open ball. And I can do it for every point in this open ball. And if the ball was closed, suppose that there's a boundary point over here, then for boundary point it will not work, because for a boundary point any neighborhood will contain points from outside and from inside the set. But since those boundary points are not included, I'm always on a safe distance from the boundary, even if I'm here. So I can always find a ball that is small enough that will still be contained entirely in this open ball. Okay. So this inequality, or this property of open balls, shows that open balls are open sense in a way that we will define. So we have seen that for every x in the open ball, we can find an even smaller open ball that will be contained in the origin ball. This is the key property of open sets in metric spaces, and in fact of open sets in general. So restating this, if we say it in the natural language, around any point in an open ball, we can find an open ball that contains this point and is entirely contained in the original ball. So, and of course, to prove this, the key property that we used of the distance function was the triangle inequality. Okay, and this property of open balls is that important, so it's valid also in any metric space. So now let us just, this can be proved in an arbitrary metric space. So let xd be a metric space. We have used the distance function. So if we get back here, we use this distance function and we use this specific properties of the absolute value. But what we really needed is this triangle inequality. So we can now take this property and show that it is valid in any metric space, and this proof goes unchanged except for changing this absolute value of the distance by a distance function. Okay, so let's see how it works. So the theorem is goes as follows. So for any metric space and any point, and r a real positive number, then for every x in this open ball, there exists a positive number delta greater than 0, such that the open ball with radius delta around x is contained in the open ball around with radius r around x0. Sorry, another typo here. So an open set U in a metric space will be defined as, so now if we want to generalize this desired property of open balls, so we will say that a set is open if around each point in the set we can find an open ball which is entirely contained in this set. So an open set U in a metric space will be defined as a set such that I've already said that for each point x in U, we can find a positive delta such that the ball with radius delta around any point in the set is entirely contained in U. So for every x, there exists a positive delta such that the ball with radius delta is contained in the set. So now if we define open sets in such a way, so a set is said to be open if around each point in the set we can find an open ball that is entirely contained in the set. So using this terminology, we have proved, this theorem says that open balls are open sets, right? Often happens in mathematics. So and let's see, as I've mentioned, the previous proof remains unchanged except for changing the metric, right? So indeed, suppose that we take, here we don't have a typo, any point in the ball with radius r around x0. This means that for this point, the distance between x and x0 is smaller than r, okay? And let us choose h to be the distance, the difference between r and this. And of course, by definition, since this distance is smaller than r, then r minus this is some positive number h, okay? And now let us choose delta to be h half. So now for every point in this ball with radius delta around x, any y that lies in this ball satisfies that the distance of y from x is smaller than delta, which we have chosen as h half. So this h is actually the distance to the boundary, if so to say, okay? And the distance of x from x0 is r minus h, and now we add those two and use the triangle inequality for the metric. And so when we add those two, this is what we get. So on the one hand, this is h over 2 plus r minus h, which is r minus h half. H is a positive number, so this is strictly smaller than r. And on the other hand, using the triangle inequality, we see that this has to be greater than the distance of y from x0. So in fact, what we have taken, we have shown that arbitrary point, any point y in a ball with radius delta around x, right, any point, the distance of y from x0 is smaller than r, which means that y lies in this ball of radius r around x0. Okay, so this is, yeah, the last sentence is just what I said verbally. Okay, so again, the definition of open sets in a metric space. So let xd be a metric space. A subset u of x is said to be open if for every point x in u, we can find positive epsilon. Doesn't matter, it was delta previously, but we can find a positive number such that this ball with this radius epsilon is entirely contained in this set u. Okay, and so we have seen that there is an actual way to define open balls in metric spaces and open sets in metric spaces. And in the essence of topology is defining what are open sets and their key properties, and more about this will be in a course in topology. But it is really important to introduce those concepts together. So now when we have a metric space xd and any point x and x, so we would say that, yeah, we want to define the notion of a neighborhood. So we say that a set W is a neighborhood of X if this W contains an open set that contains X. This is what it means to be really a neighborhood. And this is the only important thing. So again, an open set is a set such that for every point in the set, we can find a ball with small enough radius that is entirely contained in a set. And this is an open set. And now for a neighborhood of a point x is something that is some set that contains an open set. Okay. So now using this terminology, we can really give a general definition of convergence. And basically what we would say is that a sequence converges in a metric space or even in a topological space if every neighborhood of this limit, so a sequence converges to a limit L, if every neighborhood of the limit contains almost all the elements of the sequence, right? So this is the definition. So a sequence again in a metric space X is said to be converging to a limit point x0 if every neighborhood of x0 contains almost all elements of X. And so proposition, so the current definition is equivalent to the previous definitions, at least in the case of yeah, for metric spaces. And so let us make this observation. So changing any finite amount of elements of a sequence, as we've said, will have no effect on the convergence of the sequence or on its limit. So a convergence is really a property of the infinite. It depends only on the tail, on the infinite tail of the sequence, and not on its head, or not on its initial starting elements. It's an emerging property of infinity, so to say, like convergence. Okay, so now let us prove that those definitions are indeed equivalent. So again, for every epsilon that is greater than 0, the open ball with radius epsilon around x0 is an open neighborhood of x0, is in particular neighborhood, because a neighborhood is something that contains an open set, and an open set is something that contains an open ball. Okay, and this means that according to this definition, that all but finitely many elements, it's the same proof that we have previously, of the sequence lie in this ball of radius epsilon around x0. But this means, so if, again, as in the proof that we have seen, if n of epsilon is the maximal index of those finite numbers that lie outside of this ball, right, then all the elements with index greater than n of epsilon must lie inside this ball. But this means that for every n that is greater than n of epsilon, yeah, that they lie inside this ball, which means that their distance from x0 is smaller than epsilon. And so we see, again, we have proved that convergence according to this definition implies the convergence according to the previous definition, right? So we have proved that this definition implies the ordinary convergence in metric spaces. So this means that an converges to x0. And now conversely, suppose that this sequence converges to x0 according to the old definition, then it means that in every neighborhood we can find a ball of radius epsilon around x0, of course, right? Because a neighborhood is something that contains an open set that contains x0, but an open set necessarily contains this open ball of some radius, right? And this means that, so for every epsilon, this means that there exists n of epsilon such that for every n that is greater than n of epsilon, a n is in this ball. And so, again, this indicates that only finitely many elements can lie, because for every n of greater than n of epsilon, all the elements lie in this ball. This means that only elements from 1 with indices from 1 up to n of epsilon may lie outside this ball, right? And all others must lie inside this ball. So if we were to visualize this, for example, for a sequence of points in the plane, where we have a way of measuring distance, right? Then, and we were to draw this ball of radius epsilon, then similarly to what we have seen in the visualization, only finitely many elements will lie outside of this ball, and the rest will be inside. And this can be done for any epsilon. I can take this epsilon as small as I please, and again, only finitely many elements of the sequence will be outside of this ball, and the others will be inside. Okay, so let us see more examples, or let us see what it means for a sequence to be not convergent, according to definition, right? So a sequence does not converge to the limit x0, right? Again, so let us make the logical negation of that definition. So in the definition we had for every epsilon, now the negation would be that there exists epsilon 0, such that for every natural n, we can find index that is greater than this n, such that the distance between the elements of the sequence and the limit candidate, which is not the limit, is greater than epsilon 0. And in other words, it would say that it's easier to think of this in terms of the second equivalent definition, that for every epsilon neighborhood of the limit, there will be infinitely many elements that are lying outside of this neighborhood, right? So again, so we could say that the sequence does not converge if there exists a neighborhood of x0s, any neighborhood. It's enough to have any neighborhood of x0 such that infinitely many points of the sequence lie outside this neighborhood. So why we say that there exists a neighborhood? Because suppose that we take a giant neighborhood, then it could happen that this very big neighborhood, this very big set that contains an open set, it could happen that it contains, by accident, all the elements of the sequence, right? But this will not work for every neighborhood. There would be some small enough neighborhood that will miss an infinitely many, or that will fail to contain infinitely many elements of the sequence. This is the meaning of that. Yeah. So, restating it, if we look at neighborhoods around a ball, for example, with radius epsilon 0, so there would be infinitely many points lying outside this ball, right? So, for example, let us go to the sequence that we've seen at the beginning, an, which is minus 1 to the power of n. This sequence does not converge to any limit, and let us prove it, right? So first let us show that it does not converge neither to 1 or to minus 1. Of course, and okay, so an doesn't converge to 1, since we can choose, for example, epsilon 0 to be 1, right? And then all the collection of all the points whose distance from 1 is smaller than 1, it is this interval from 0 to 2, right? And so all the elements of the sequence with odd index, they will be equal to minus 1, and they're lying outside of this interval. So epsilon 0 can be chosen here as 1, and then if we choose epsilon 0 to be 1, then infinitely many elements, right, of the sequence will lie outside this interval, right? And similarly, we can do the same for -1, right? So in the sense of the definition, for every number that you choose as big, you can choose a number as big as you please. You can always find an index that is bigger than this number, whose distance from such that the element with this index, its distance from 1 will be greater, for example, than this 1. And similarly, it's with -1, right? So because here we have this sequence from 0 to 2, this interval of 0 to 2, this open neighborhood of 1 from 0 to 2, fails to contain infinitely many elements of the sequence, right? Okay, and so similarly, the sequence does not converge to -1. So let us show that it cannot also converge to any other value, okay? And so if a is not 1 or -1, let us denote epsilon 0 to be the minimum of a minus 1, or if a is this limit, right? If a is any number. So let us consider a minus 1 and a minus minus 1, which is actually a plus 1 in absolute value, right? So this is the distance of a to 1, and this is the distance between a and minus 1. And so if a is neither of those, then this is going to be some positive number, okay? But then choosing this epsilon 0 implies that for every n, we have, for this particular sequence, because it's either 1 or -1. So, of course, choosing epsilon 0 like this, we see that for every n, we will have that the distance of a n from n is greater than epsilon 0, and therefore the sequence does not converge.